speaker off here. Okay, so we ended up with the population as a function of time was going to be equal to 2,000 divided by 1 plus 9 times e to the minus 0.254 k. And then the last part of the problem asked for, what did they ask for? What is the population after 20 years? So that's just a matter of sticking 20 into the equation. So go ahead and calculate that. 1 plus 9 e to the minus 0.254 times 20. So I was checking out Perry McClure's basketball record this year and their scores. Does anybody know how they've lost one game to Floyd County, but otherwise they've beat almost everybody by about 60 points. I've never seen such lopsided scores, consistently lopsided scores. It's yeah, I mean these are like Craig County or Highland County, but I don't remember the exact score, but it was like 90-12. I don't know. Was it that bad? I don't know. It sounds about right. So, I was telling, I said to Martha this weekend, I said, I need to go see them play. So you've got a game against Botetourt, which would be one of probably your hardest game, right? So I think we're going to go to, we got some stuff to do in Roanoke, but I think it's at 3:30, I think. Is that right? Yeah, so I'll probably come and watch you guys play Botetourt. It's hard to know. Yeah, I guess your practices are probably more challenging than the games. So yeah. Okay, so what do we get for the answer? Anybody? Anybody who doesn't look like they're working must have the answer. Maya, what'd you get? 1892. Okay, I'll assume that's right unless somebody says otherwise. Oh, is it after 30 years? Oh. Oh, did I write it down? What did I? Oh, I just wrote that down wrong. So was that after 30 years or 20 years? Okay, what's it after 30 years? 1990? Okay. So whichever one you did is fine. So Margaret, we watched Zookeeper's Wife last night. It was good. Yeah, it's worth getting. And I was I was looking for my Netflix queue, which is pretty short because Martha doesn't like science fiction. She doesn't like horror. She doesn't like so pretty much it's down to romantic comedies, and this one wasn't a romantic comedy. So this was it was historical fiction. It was pretty good.
So last night I printed out all the Oscar Best Picture winners ever.
Yeah.
And I've seen 5 of them, so I'm not doing too well. There are like 10 on Netflix, so I just have a big list.
Okay. Yeah, I went through probably 300 movies and only was able to pick about 6 out that I thought Martha would be interested in. Even some that she wouldn't, like Rogue One. She's not interested in Star Wars, and I haven't seen Rogue One. So, but yeah. So the Zookeeper's Wife. Not to give away the story, but it's about this zookeeper and his wife in Warsaw, Poland, who help save Jews during the World War II. So it's pretty, it can be, I mean, it's not like I haven't watched a lot of Holocaust movies, but you know, it's reasonably graphic, but not over the top kind of graphic. I don't think. It's just, yeah. Anyway, you can watch the movie if you want to. So it was.
I really like Jessica Chastain.
Yeah, yeah, yeah. Because she's doing a. I think she was doing a Russian accent because it was Poland, but they were from Russia originally.
She was just, I don't think this one will be in the Best Picture nominated queue, but she was in this movie called Molly's Game, where she's kind of a high stakes poker dealer.
Oh,
And
really?
it looked interesting, but I didn't see it.
Okay, so let's see. We got how many more problems we got left on this bar? Two, right? Right. I think we got one that we didn't do. Yeah. So two, actually three. Right? Three? No, two. We did. Did we do this one? Oh, okay. So we got three left to do. Let me borrow this for just a second. So so we're going to go to the back of the first page, which is separation of variables. So you would normally try to separate variables. If it doesn't work, then you can try see whether it's a homogeneous equation, but it's this one. Okay. So they give you an initial condition, which means that you can find the particular solution. But the first thing you have to do is find the general solution. So what you're going to do is you want to change y prime to dy dx. And then you can multiply everything by dx. And then move stuff around. They should end up, both sides look pretty much the same once you separate them as far as the integral. And the integral you will have to use u substitution on both sides, but it'll be the same u substitution. So here's step number one. What? Yes?
I think the paper says y of 0.
Oh, is it y of 0? That probably makes sense. Yep. Yeah, thank you. Y of 0 equals, yeah. Can't even read my own writing. Okay, so you're going to change y prime into dy dx. Step 2 is you'll multiply by dx just to get the dx out of the denominator. Step 3 is separate variables. Step 4 is integrate. Yeah, so you can divide by that and divide by that, and you should get all the stuff. Oh, well, while you're doing that, I still have a few left here. I just hadn't.
So for this part here, I've changed this into 1/2 of these
Right.
parentheses. And I can't
Well, it's
remember
to the you're going to divide by those though. So you still got you got to divide by the square root of 1 minus x squared and divide by that. So this should be in the denominator, and then it'll be to the minus 1/2 power.
Oh, yeah.
But you actually want to do the u substitution before you do that. Oh, my microphone's not on. There we go. There we go. I didn't turn my microphone on. And I did have my obligatory tears during that. uh, so to go from here to here, you're going to divide both sides by 1 minus square root of 1 minus x squared, and divide both sides by square root of 1 minus y squared, so you end up with that. And so you're going to have the y and dy in the numerator, this in the denominator, and the same on the other side. So the u substitution, as I said, is going to be equal to 1 minus y squared, and then du is going to be equal to negative 2y dy. Same over here. And you can cancel these out, at that point when you've made the u substitution. And then you're going to use the power rule here. Add 1 to the exponent divided by the new exponent. And remember, the initial condition was, what was the initial condition? Y of 0 equals 1/2. I'm just writing it down so I don't have to go back. You won't apply that until you've actually integrated. And you don't have to, you don't need to explicitly solve for y in this case, but you can still solve for the arbitrary constant. It's just a little different. Normally you just have y equals something and you set the left-hand side equal to y. In this case, you're going to substitute in what y is equal to. Which is not going to be, it's not just a simple calculus, not super simple. I just left it as a radical here, but what happens here, you've got the square root of 3 over the square root of 4. Square root of 4 is 2, so the 2's cancel out. So you're just left with the square root of 3. And you've got the negative 2 from there. And then you plug it back in. So this initial thing, this is your particular solution. And then this is your, sorry, wrong way around. This is your general solution. And this is your particular solution. Okay, let's move to the next problem. I have to borrow your paper again. We've already done 2 of these, so this is just the same kind of thing that we did the other day. So I'll give you another practice. And let's just solve it till we get to where they're separable, and then we'll work through the other part together. So the substitutions that we make are y is equal to nu x, and dy is equal to nu dx plus x d nu. So remember, you get rid of all the parentheses, simplify it by combining like terms, and then if there's a common factor you can divide by, which I'm sure there will be. And once you get to that point, then you can separate the variables being nu and x instead of y and x. And I can't read my writing again here. What was this, squared or cubed? Oh, that's prime. That's neither one. I was like, what am I doing here? Writing too fast. Prime. Okay. And again, is it homogeneous? Looking at it, we can run that test where you let x equal f of x. You look at f of x versus f of x and y versus f of t times x and t times y. But again, looking at the original equation, you've got x times x squared, which is something cubed, basically. If you're talking about units, then you've got x squared times y, which is something squared times the single power. So that's there's 3 of those as well, and then x cubed. So they're all essentially from a unit standpoint, they're all cubed. I always think it from units. If they're all meters, you'd have meters cubed plus meters cubed plus meters cubed. And that has to happen for it to be homogeneous. So it is homogeneous. So remember, first thing you do is you change y prime to dy dx. Just like we did in the previous problem. Step 2, multiply by dx. Step 3, substitute. Step 4, multiply out. Step 5, simplify. Step 10, go back and check your algebra. More than once. Just take your time the first time. And I always tend to, when I multiply everything out, I tend to, I have the constant first, then I have x to some power, then I have nu to some power. That way they're in the order that you can kind of compare them better. If you just leave them in the order that you multiply them out initially, you may have a hard time recognizing if there are ones that have the same are the same type. So when I multiply these out, just how I keep them straight is I just kind of go to each element and count them as I go. So I do my x's first. So I've got x, and then I've got x squared. So that's x times x squared is x cubed. And then I've got new squared. So it's new squared. So I've done everything dx. Okay, now the next one, you've got these three terms. So I take these terms and I count again. Well, there's only one constant, which is 2. So I bring that down. And I've got x squared plus 1 more is x cubed plus 1 more is x to the fourth. And then I'm done with the variables. So that's x to the fourth. And I go back through and then inventory the news. So I've got only one. You can see I only have one new. And then I've got d new. And then I do the second bit here. So again, I've got the constant 2. So I bring that down. I've got x cubed times x, which is x squared times x, which is x cubed. I get over here, I don't have any more x's, so I write down x cubed. And then I go through with the news, so I've got new here, and then I've got another new there, so it's new squared. And then I go to the dx, or the d new part. And then the right-hand side, there's nothing. It's just 5x cubed dx. And then I look to see if there were any terms that had the same form. And because I put it in the same order, x's and then news, I noticed, oh, I got an x cubed new squared in both of those. So I combined those two into 3 x cubed new squared. So that's the combining terms. And then you can usually divide by something, which is what the next step was. So then you divide each term by x cubed. So you get 3 new squared dx plus 2x new d new is equal to 5 dx. Okay. And then you can move all your dx's to one side and all your d news. In this case, you only have one d new term. In this case, here you can factor out dx, so you get dx times 5 minus 3 new squared. And now at a point like we did in the previous problem, you can just divide by x to get the x's over here and divide by that to get the news on the other side. So you'll end up with 2 new d new over 5 minus 3 new squared is equal to dx over x. So there you go. So it's separated now. And the way this one's the natural log of x, and this one would be you'd have to let u equal 5 minus 3 new squared, and you would have du would be negative 6 new d new, and you'd factor out the two like you normally do. This is going to end up being something times the natural log of 5 minus 3 new squared. But we'll just stop there. We won't go. Okay, now to the last problem. So let me borrow your paper again there, Cassie. Yeah, so the test next Tuesday, chapter 6. There's usually 5 problems. One is separation of variables. One is homogeneous, just like we did. One is exponential growth or decay. One is logistic growth. And one is first order linear differential equations solving using the integrating factor, like this. again, this one gives you the initial condition, so we should be able to figure out what the constant c is. But and must be an equal sign there, not a plus sign. It's like I'm missing something. Okay. So the first thing you do on these, in this case, we want y prime. It's kind of funny because all the other ones we wanted to break up into dy dx, but really you want to have y prime. So we're going to divide both sides by dx first. So you'll get x times dy dx is equal to x plus 2y plus 2. And then you'll make dy dx into equal y prime. So that's so you might write a little note that says for first order linear differential equations I want y prime, whereas all the other stuff, all of the separation of variables, we want dy dx. So if you remember back, what we did is the first thing you need to do is put this in standard form. And standard form is y prime plus p of x times y equals q of x. So you notice that there's a term y prime which needs to be on the left-hand side of the equation, which it is. There also should be a y term which is here, so it's on the wrong side. So you're going to want to move this term to get to the other side. And you'll also notice that my y prime term has an x in front of it, so I'll want to get in standard form. Once I move this to the other side, I'll need to divide everything by x to get into standard form. So go ahead and do that little bit of manipulation there. Get it in standard form. Did I officially assign anything from section 4 yet? Okay, I need to. So while you're doing that, I'm going to give you the homework assignment for this section. There it is. Is Mr. Graham doing anything this week? Do you know, for you guys? Have you heard anything? Okay, because he'd asked me if you guys had a test this week.
He wants to bring someone in from Dabney to talk about scholarships.
Oh, okay. Okay. Okay, we'll move it back here. See if you got that. So that's standard form right there. So I moved the 2y to the other side, became negative, divided by x. So x divided by x is 1, 2 divided by x is 2 over x. Okay, the next thing you're going to do is you identify p of x. That's the coefficient in front of, or the term in front of y. And the integrating factor, which is the thing that we multiply the entire equation by, is e to the integral of p of x dx. So you stick that in there, integrate it, and get u of x down here somewhere. So give that a try. Remember that you don't include an arbitrary constant when you integrate it. Just leave the arbitrary constant off. Okay, so just stick p of x in there, then figure out how to integrate negative 2 over x dx. Where are you on that? Okay. Negative of, yeah, there you go. So when we integrate this, the negative 2 comes out of the integral. The integral of dx over x is the natural log of the absolute value of x. So what did we do the other day? Because we need one more step here before we get... We had something similar to that. Not exactly. So Evan, what did you do? The negative 2. Did you do? So it's so you took it inside the log? Yeah. Yeah. So you before what we had plus 2 times the natural log of the absolute value of x. So what we did before was we took that inside and we squared it, but in this case it's negative 2. So instead of having it to the second power, you have it to the negative second power. So this becomes e to the natural log, the absolute value of x to the negative 2 power instead of the second power, which is the same as 1 over the absolute value of x squared. And again, because it's squared, whether it's in the denominator or the numerator, you can remove the absolute value, so it becomes e to the natural log of 1 over x squared. And at that point, the only constant in front of the natural log is 1, so then you can use the inverse properties of logarithms and exponents, and so the answer is 1 over x squared. So that's my integrating factor. So what you do with your integrating factor is you take it and you multiply the entire first order linear differential equation in standard form by that integrating factor. So we're going to take 1 over x squared and we're going to multiply it by y prime minus 2 over x times y is equal to 1 plus 2 over x. So if you multiply this thing out, you get 1 over x squared y prime minus 2 over x cubed y is equal to 1 over x squared minus 2 over x cubed. Now at this point, a lot of people don't ever check to see whether if their answer makes any sense or not. You know, they do this part right or they do it wrong and then they just plug it in and then they end up with a big mess. So what you want to do, remember, is we're trying to take two terms and combine them into one term. And the only way that works is if this is the derivative of that, which it is, because this is y and this is y prime, and this is the derivative of that. So if we take this term, 1 over x squared, once we've multiplied out with the integrating factor, if you said what is the derivative with respect to x of this term, which is 1 over x squared, that's the derivative with respect to x of x to the minus 2 power. So when you take the derivative, you take the exponent, reduce the exponent by 1, and if we rewrite that, you get negative 2 over x cubed, which is that. Okay, so it does work. And if it doesn't work, then the next step is completely wrong, and you may end up having integrals that you can't do. So it's probably worth checking that. So now that I know that's true, then what you can do is you can combine these two terms, and you take not the derivative, but the original values and multiply them together. So what you'd have is, the original value here is y. I'll put it right here, y. And then this is the original, that's the derivative. So it's 1 over x squared. The whole thing primed is equal to the right-hand side. And at that point, then you're good to go. Then you integrate. Actually, you multiply everything by dx, so times dx. So you'll end up with 1 over x squared y quantity prime dx equals the integral of 1 over x squared minus 2 over x cubed dx. And because this is the derivative, integral of the derivative, you just rewrite it without the derivative or the integral. And then the right-hand side is just your normal integrals. So this is x to the minus 2 power. This is negative 2x to the minus 3 power. So I rewrite them as exponents in the numerator. So the integrating, you add 1 to the exponent, divide by the new exponent, add 1 to the exponent, divide by the new exponent, add your arbitrary constant c. Let's clean it up a little bit. So you get 1 over x squared, y is equal to negative 1 over x. Plus, this cancels out with that, so you'll just get plus 1 over x squared plus c. So you can see that, and it's always this way. You can in first order linear differential equations, you can always solve explicitly for y, because you're always going to just end up with y here. You're not going to have y squared or anything like that. So in this case, we will solve for y explicitly. So what that means is to solve for y, I'm going to multiply everything by x squared to make this go to 1. So this gets multiplied by x squared. This gets multiplied by x squared, and the arbitrary constant gets multiplied by x squared. So we'll say multiply by x squared. You get y is equal to negative x plus 1 plus cx squared. Again, when you have solving first order linear differential equations, you always end up with the arbitrary constant either multiplied or divided by, well, always multiplied by the integrating, or divided by the integrating factor. So that's the general solution. And then you can use your initial condition, which I can't remember did we have one? I think we did. Yeah, y of 1 equals 10. So now we use our initial conditions. So you take y of 1 equals 10. So 10 equals negative x, which is 1, plus 1, plus c times 1 squared. So c in this case is equal to 10, because those cancel out, and you have a coefficient of 1. So the final answer, this is the particular solution, is negative x plus 1 plus 10 x squared. So again, this is your particular this is your did it again, wrong way around. That's your general. That's your particular solution. So what we're going to do tomorrow is we're going to look at one more kind of problem. It's kind of an extension beyond first order linear differential equations. It's for nonlinear first order linear differential equations that are special kind. They're called Bernoulli's equations. So it's kind of like homogeneous. You have to transform it first before you can use the integrating factor. But it's reasonably, I mean, it's as hard as this, but add something additional to it. Luckily, I don't put that on the test, but I like to show it just to show you, just again, to give you a flavor of what differential equations courses are like. They do get kind of complicated. Okay, so that's it for today. We're going to talk about capacitors I actually have a little lab to do today. So I made it up yesterday or Friday. Hopefully it goes okay.